Now continuing with this question, we're going to take a look at these two scenarios separately. So let's focus on the first case where b is equal to 0 and ka is going to be equal to j pi, where j is equal to 1, 2, 3, and so on. So when b is equal to 0, our xi of x, we can actually take away this term, because when b is equal to 0, I can just take away this cosine term. So in the end, our xi of x is going to be equal to a sine kx. So this is what our xi of x is going to be equal to. And then we can substitute in k, which is equal to j pi over a. And then I'm going to manipulate this a bit by multiplying the numerator and denominator by 2. And the reason I'm doing this is because, first of all, I want the denominator to reflect the width of the well. So if you take a look at the infinite square well, the width of this well is actually equal to 2a. So that's why I'm putting this in the denominator. And later on, tacking a 2 onto the j is going to be useful later on. So you'll see that when we're dealing with the energy levels. So this is what our xi of x is going to look like. And then notice that ka is equal to j pi. This expression actually gives us the allowed energy levels as well. So don't forget, k is equal to the square root of 2me divided by h bar. So ka being equal to j pi, with a bit of rearranging, I can square both sides, so that would give me k squared. I have j squared pi squared divided by a squared. And then on the left hand side, this term is just equal to 2me divided by h bar squared. And then like before, I'm just going to tack on a 2 to these two terms, so that 2a is going to reflect the width of the well, which is equal to 2a. So I'm just multiplying the numerator and denominator by 4 in this case. So this is what you have on the right hand side, and this is what you have on the left hand side. And then dumping the rest of these constants to the right hand side, you see that the energy levels, the allowed energy levels, E is equal to 2j squared times pi squared times h bar squared divided by 2m times 2a squared. Now you can compare this expression with the energy levels of the infinite square well in the example that Griffiths gives us. And for Griffiths' example, the energy levels that he gets is given by this formula. And you can see that it's different because of these two terms over here. So in Griffiths' example, his well had a width of a, and now our well has a width of 2a, so these are pretty much the same. And instead of a 2j squared, he has an n squared over here. So I'm just going to redefine 2j to be equal to n so that I could match his notation. So the energy level n is equal to n squared pi squared h bar squared divided by 2m 2a squared, where n is equal to 2, 4, 6, 8, and so on. So all even numbers. So for Griffiths' expression for his energy levels, n can go from 1, 2, 3, and all the way to infinity. So it includes all integers. But for us, n would only include the even numbers, so 2, 4, 6, 8, because j itself goes from 1, 2, 3, and so on, so all natural numbers. And then here we're defining n to be equal to 2j, so that's why for our n, it can only take on the values, take on even values. So you might be wondering where the rest of the values are. Where are the 1, 3, 5s, and so on? So they would correspond to this second case that we have over here. So you'll see in a minute that we will be able to derive the rest of the energy levels. But so far for the case, if we assume that this condition is satisfied, we see that our xi of x is going to be equal to this expression, and we see that our energy levels will be given by this formula over here, for n is equal to 2, 4, 6, 8, and so on. And you can see that this expression matches the expression Griffiths obtained perfectly, and which is what it should be, because all we're doing is that we're shifting the infinite square well over slightly to the left, and we're expanding it by a bit. So in the end, the physics should be the same, and that's why we did indeed arrive at the same formula for the energy levels. So we can actually also rewrite this xi of x by using the notation n. So we have n pi divided by 2ax. And so for the case, when we assume that these requirements are true, then we see that our xi of x is going to be equal to this expression, and it will have energy levels. It will have energy levels equal to n squared pi squared h bar squared divided by 2m 2a squared, and n will be able to take on all even number values. So this is pretty much the solution for the infinite square well, or half of it, because we have only derived half of the energy levels. So you can see that we still have one unknown remaining, the normalizing constant. So we can just quickly derive this by integrating the integrating xi of x. So we integrate it from negative a to positive a, and then we have a squared, and then we square the sine term, so we have sine square n pi divided by 2a times x dx. So we would restrict this integral to be equal to 1. So integrating this, I can just pull this constant out. Integrating a sine square, this is an even function, so I can just put a 2 over here, and then change the bounds from going to 0 to a. And then for the sine square term, I'm going to use the double angle formula. So recall that cosine 2x is equal to 1 minus 2 sine square x. And since we have a sine square x is equal to 1 minus cosine 2x divided by 2. So with this term, I can rearrange this as 1 minus cosine 2x, so I just multiply 2 to here, so I get n pi divided by ax, and then divided by 2 dx. And then these 2's, they cancel out. So integrating this expression over here, integrating 1 from 0 to a, I get a, and integrating cosine, I get sine n pi divided by ax times a over n pi. And this will be evaluated from 0 to a. So sine, if you substitute in a, you get sine n pi, which is just equal to 0. And then if you substitute 0, you get sine 0, which is also equal to 0. So this term is equal to 0. So you see that a squared times a is equal to 1. And so that's why our normalizing constant is 1 over the square root of a. And so we can now express our solution fully. So we have found all the unknowns. We know that, so recall that originally our problem, we had 3 unknowns, a, b, and k. And we found that for the case when b is equal to 0, so that's the first unknown, the normalizing constant is equal to 1 over square root of a, that's the second unknown. And then the k, which is related to the energy levels, has also been found, because we have also found the energy levels. So you see that all 3 unknowns have been found. So this is the first case. So now we're going to focus on the second case. We're going to do pretty much the same thing, and now we're going to focus on the second case. So for the second scenario, a is going to be equal to 0, and ka is equal to j minus 1/2 pi, where j is equal to 1, 2, 3, and so on. So all natural numbers. And if a is equal to 0, our xi of x is just going to be equal to b cosine kx. And then once again, I can just substitute, instead of writing k, I can write this as j minus 1/2 x divided by a. And then I'm going to do something I did as before. I'm going to multiply the numerator and denominator by 2, so I get 2j minus 1x divided by 2a. And so there we have it. This is what xi of x is going to be. And then once again, I'm going to take this expression, and then I'm going to derive the energy levels. So we know that ka is equal to j minus 1/2 pi, and k is just equal to the square root of 2me divided by h bar. And now I'm going to dump the a over to the other side, which would give me 2j minus 1 pi divided by 2a. So you can see that I've multiplied the numerator and denominator by 2, and then squaring both sides and dumping all the terms over to the other side, I get 2j minus 1 squared pi squared h bar squared divided by 2m 2a squared. So once again, compare this with Griffiths' formula. You can see that it's pretty much the same thing. And so there we have it. You can see that we have indeed obtained the energy levels for the infinite square well. And then once again, like before, I don't like writing 2j minus 1. So for this case, j is equal to 1, 2, 3, and so on. But instead of writing this, I'm going to define n to be equal to 2j minus 1. So now I can rewrite this expression as n squared pi squared h bar squared divided by 2m 2a squared. And this time, n is going to be equal to 1, 3, 5, and so on. So you can see that if you substitute 1, you get 2 minus 1, which is equal to 1. You substitute 2, you get 3. You substitute 3, you get 5, and so on. And so these are the energy levels for the infinite square well for the case where a is equal to 0. And you can see that we have derived the rest of the energy levels. So just now, we only found the energy levels where n is a even number. And now, by considering the second case, we have obtained the rest of the energy levels. So it seems like my laptop is running out of batteries. We just charge it. So let's continue on with this. So we're basically done over here. You can find the normalizing constant. If you go through the process that we just went through just now, you can integrate this function and you'll find that b is actually equal to 1 over the square root of a. And then for this term over here, I'm just going to write this out as n, so it seems like I left out a pi, so n pi x divided by 2a. And so there we have it. This is going to be our xi of x. So we're basically done with this question, so let us just summarize what we have so far. So right now we know that our xi of x can be equal to two different things. It could be equal to 1 over square root of a sine n pi x divided by 2a. So for this case, n is going to be equal to 2, 4, 6, 8, and so on. And then when n is equal to an odd number, you're going to get a cosine. So cosine n pi x divided by 2a, where n is equal to 1, 3, 5, and so on. And then for the energy levels, we have found that for both of these cases, they both follow the same formula. Divided by 2n times 2a squared.